Moving forward, our next topic is we're going to cover at least the basics of deep neural networks and how to use these as function approximators. Well, in the hopes of integrating them with the reinforcement learning methods that we've seen so far and maybe some new methods that we're going to learn moving forward. This topic will cover, as I said, the basics of deep neural networks. For some of you it will be less helpful if you have a lot of experience and you know a lot about previously learned about and previously used deep neural networks. It might be pretty straightforward for you. For those that have less experience, this will give you the required background in order to implement deep reinforcement learning algorithms that we're going to learn on later on. Okay, so some to-dos. Please be sure to be on top of your assignments. At this point you should already have submitted or are working towards the end of the Monte Carlo control algorithm with and without important sampling, tabular Q-learning, SARSA, and now you should also start working on the Q-learning with approximation implementation. You have a quiz available regarding value approximation, and you should start finalizing your project proposal. So as I said earlier, we're going to continue to discuss function approximators today. Specifically, we're going to describe the main function approximator that we're going to use throughout this course, which is a deep neural network. So just as a reminder, we use function approximators as mappings from some x, usually a vector representing our state, possibly with action if we're trying to approximate Q values. If we're trying to approximate state values that only a state, the x is the input to our function approximator, so that would be the state, and y would be the state value or action value if we're trying to learn Q values. Y, right, we'll learn more ways that we can actually use function approximators later on, where y can also be an action if our approximator is trying to approximate a policy. And again, we will see this later on and how to optimize the policy. We saw this before, right? We saw one approach where we converged directly on the policy. What was the name of that algorithm?
Squares TD?
Policy iteration, right? So later on we'll also see how we can do policy iterations with approximation while approximating the policy. We'll see this later on. So in general, we will consider 4 different approximation tasks throughout this course. We might do state value approximation. We call it V hat, where V hat is our deep neural networks mapping states to values, right? A specific state value for each one of these states. We'll see action value approximation. This is the Q network, a Q approximation, mapping state and action pairs into Q values, right? Also a real value number. We'll see, as I just said, we'll see later on some policy approximation networks that approximate policies. We'll call them pi with a hat, that maps state into actions. Or, this is something that I mentioned before, we might be learning soft policies, which map states into, you remember?
A distribution of actions. A
distribution over the actions, right? So some probability for each one of the actions in discrete spaces. Or if we have continuous actions, this can be a distribution over the action space. This will be soft policies, so we'll do both of them in policy approximation. And we might also we'll probably look at some model approximation for model-based approaches. So we might use a deep neural network in order to approximate the model. And that will be a mapping between a state and an action to the immediate reward, right? This is approximating the reward function, and to the next state, or a distribution over the next states, okay? To represent the transition probabilities, the model. So in general, a neural network is a function, f hat is a function approximator, with many parameters, with many tunable parameters, and we'll call them theta in the general case. that can be, these tunable parameters can be tuned to approximate any well-behaved function, f, the one that we are trying to fit, with arbitrary accuracy. This is true for under some conditions that you have sufficient number of neurons or per layer, or sufficient, actually in a two-layer deep neural network, or sufficient number of layers in a fixed depth, fixed width neural network. We won't go into that. Again, I'll just give you the basic of deep neural networks, the basics that you need in order to actually implement the deep RL algorithms that we'll discuss later on. Of course, there is a much deeper literature and meaning behind deep neural networks that we will not cover in this course. Okay, so let's start from a single perceptron, right? The simplest unit that builds a deep neural network. So a complete deep neural network will be a combination of many perceptrons. Let's start with a single perceptron and work our way upwards. So this is a single artificial neuron. It is actually, at the end of the day, just a linear approximator. We'll see how we can make it non-linear, but in a second. The tunable parameters for a single perceptron, are the weights, right? So it's a linear approximator, so it only has a weight vector. And the output is the dot product between the input vector, call it x in the general case, and the w vector. Okay, our goal, of course, is to set the w vector such that our linear approximator would resemble as closely as possible to the real function that we are trying to fit. So the approach that we're going to use in order to train this approximator would be to minimize the difference or the loss between our approximation and the function that we're trying to fit. That is, we're going to minimize the sum of errors, the sum of differences for all of the training point. Or if we just try to minimize the sum of the errors, we know that this is also known as the L1 loss, or the absolute error loss. This is not a differentiable equation, a differentiable loss function, which we usually require. And so instead of that, as we said previously, we're going to minimize in most cases that we are concerned about, we're going to minimize the squared error, the sum of squared errors. This is also known as the L2 loss function. So let's say that we're trying to train a perceptron in a way that minimizes the squared loss function. As before, as we discussed previously, we can use the gradient descent method, right? Where we update each one of the tunable parameters vector based on gradients in the loss function with respect to these tunable parameters, right? And as we saw previously for temporal difference learning, for TD learning, this value here, the derivative of the squared loss function is similar to the TD error, right? And this is also the case for the Monte Carlo approach. We've seen that before in the previous topic. And in those cases, the function approximator is either approximating the state values or the Q values, the action values. With a linear approximator, a single perceptron, the gradient in our function approximator is simply the feature vector, or the x, the input to the function approximator, to the deep neural network, to the perceptron. It's not a deep neural network yet. If we are considering a linear approximator, it enables us to compute a closed form, to compute the optimal point as a closed form, in a closed form expression, right? And we saw this before with the least squares TD method, or in general, we can use a least squared method to minimize the squared loss function over any set of function, right? Hopefully you learned this in your undergraduate studies. So what would be the limitation of a perceptron function as a function approximator, of a linear function approximator? The main limitations are that it is only able to capture linear relations between the state features and the output. And also the approximated linear function must be zero for an input vector which is all zeros, right? You cannot choose a different weight vector that will get you an output that is different than zero. So a linear function approximator, a vanilla one, must go through the origin in any case. So a simple way to address that issue would be to add a bias term, and this can easily be done. We usually do this. So as we said, a simple perceptron captures linear functions that pass through the origin. The solution would be to add a bias term, call it small b, that allows us to push the linear function away from the origin. How do we train the bias term? So we can still use gradient descent as before. We just need to compute now the derivative of our function approximator with respect to the bias term. But you can see that the bias term here is added regardless of the input vector, right? It can be a state or any input vector in general, right? So as a result, the gradient of our approximator with respect to b would be
1.
Just 1, yeah, it's always 1. So indeed, it's very easy to compute the gradient in our loss function with respect to the b parameter, the bias parameter. Right, so this is a simple fix to push away our linear approximator from the origin. Okay, so now we're trying to go beyond linearity, right? So the assumption about linearity is a very limiting assumption. We would like to capture or to fit functions that are far more complex than a linear function. So let's try to address that. Let's try to connect several perceptrons to combine a network. So in this case, x will be the input vector as before. Zi would be the output, or also known as the activation vector for layer I. Okay, so that would be the value in each one of the layers. As you can see, this is still a vector. Wi would be used to represent the weight matrix for layer between I-1 and I. Okay, so for instance, W1 here is a matrix of all of the weights between our input and all of the perceptron in layer Z1. As a result, the dimensionality of the weight matrix would be Zi-1 and Zi. So for instance, what would be in this case the activation in this example here, the activation for layer 1?
It would be the sum of the linear combinations of the weights?
Sum of the linear, in matrix notation, what would it be?
Wi into Zi minus 1?
So the input vectors times the weight,
So,
the first weight matrix.
So in the first, for Z1, yeah, layer 1 will be input vector into
Right,
W1. Sorry, I didn't say layer 1.
Okay,
I thought
good.
general layer.
Right, and as you said, we can do the computation per neuron, or perceptron if you would like, in layer 1. Z11 is xi times W11, right? So it's just a dot product of the vectors, but of course we can use a matrix notation and say that the entire Z1 vector is x, the x input vector, times the W1 matrix. Okay, and of course we want to, at the end of the day, represent everything with matrix notation, specifically when we code everything, because it's much more efficient, so matrix operations are done more effectively, more efficiently compared to iterative computations, right? They can be done fairly quickly using standard libraries in Python, such as NumPy or whatever. What would be the activation of Z3? So what would be our output here in this
Z2 into W3?
Z2 into W3, right? But if you start from X, so it will be X W1, W2, W3, right?
Yes.
So you can combine everything together. It will be X times W1, the results times W2, and the result times W3. And that will be the output of our network. Great! So now we have a network of perceptrons and we can compute the output moving forward. However, right, and this translates into the different activations in each layer. However, matrix product, note that matrix product is associative. That is, you can push away the, you can move the, how do you call these? The brackets, right, around. Meaning that I can rewrite this as X, our input vector, times some W prime. What is W prime? It's just a multiplication of these weight matrices. So what did we get?
Get X into W prime, right?
We get a linear approximator. Specifically, we get a linear function. So you just have a fancy way to write W prime. It's just some multiplication of several W's. But at the end of the day, this is a linear function. So we combine several linear functions just to get a linear function. Right? A more complicated representation of a linear function at the end of the day.
Does it have the ability to fit better functions though? Just because it's bigger? It's still linear.
No, it's a linear function. It's not stronger than X to the W whatever.
Okay.
It's just a linear function. You can fit linear functions to it.
And we could do that with the perceptron too.
Yes.
Single perceptron.
This is not stronger than a single perceptron. Right. So it's not more powerful than a single perceptron. Okay, so our goal of going beyond linearity, so far we didn't do very well. Okay, and so now what we have to do is to introduce non-linearities. So in order to represent general functions, the output of a neuron, of a single neuron, out of the perceptrons that we're tying together, needs to be non-linear with respect to the activation, to the Z value. Okay? And so this requires us to introduce what's called activation functions. Let's call them G of Z, and they are affiliated with each one of our neurons, or the perceptrons that we are combining together, or better known as neurons in a large network. So now the output in each neuron will be G of Wx plus P, of the linear combination. But we add some nonlinearity on top of the linear combination. Okay? So let's see what do we require from an activation function, or what we would like to see from an activation function. So first of all, we would like it to have well-defined gradients. We want it to be differentiable. Why?
To get the gradient?
To later get gradients with respect to W's and B's, right? To be able to tune our network, we want the activation function to be differentiable. More than that, we would like the gradients to provide some informative values. So we would like to avoid, asymptotic function that gives you a gradient of 0, or some exponential functions that give you a gradient of infinity. We'd like the gradient to have some reasonable values that can tell us how to improve, how to update our tunable parameters. Next, we would prefer it to be monotonic, right? And the reason is we would like to reduce the number of local optimums as much as possible, because we would like to eventually converge or find the global optimal for all of our, or to avoid, at least to avoid local optimums for our, the best assignment for our tunable parameters. Next, it should be fast to compute. It's a very intense working environment, specifically if you have very big networks, right? And finally, we would like it to cover the required output range. This might not be relevant for initial layers, but the layer, at least the final layer, should have relevant output to the values that we are trying to get out of the network. For instance, we're trying to approximate probabilities. Well, it would be nice if our activation function would provide values, would squash everything to values between 0 and 1. These are the relevant range. Okay, let's look at some candidates for activation functions in this case. So common activation functions include sigmoid, the hyperbolic tangent, and the ReLU function, the rectified linear unit. These are common activation functions, like go-to activation functions, but the literature is full of many more activation functions that might be relevant in different scenarios. So let's see if these activation functions are good candidates for the requirements that we just defined. First of all, do they have well-defined derivatives? So the answer is yes. You can see here on the definition for each one of these activation functions. For sigmoid, for instance, this is the sigmoid function. The sigmoid function has actually all of these, the sigmoid and the 10H function, they have a deeper theoretical meaning, how we got to these specific functions. But I covered that in my machine learning course. You're more than welcome to attend that. We won't go into the theory behind these functions. There is some theory behind this function. So for instance, the sigmoid function is a well-defined function, and it has well-defined derivative, right? Provided here at the bottom. And this is the case for all of them, I guess, except for the ReLU function there at the left, which doesn't have a well-defined derivative at 0, right? This is where we just connect two linear functions, which is fine. We connect two linear functions, it's still overall a non-linear function. But we have to define the gradient, the derivative, at the 0 location. So we simply define the derivative at that point as 0. Okay, so if z is greater than 0, the derivative it would be 1, else it is 0. Are the gradients informative? Well, could be better, but they're not that bad. They could be better because you see that the sigmoid and the 10H function have some regions where the derivative tends to 0, and it might be very low, which might prove difficult to make progress in these regions, right, towards the true optimum. And the ReLU function also has a large region where the derivative is 0, which is again not very informative in finding or minimizing our objective function, our loss function. By the way, for this reason, there is another version of the ReLU activation function that is known as leaky ReLU, which does define a very small gradient for the region to the left of the 0. Okay. But in any case, actually the ReLU function as is, the basic ReLU function is, I would say, the most common activation function these days. I would say this would be the go-to function that most people use. Next, you can see that all of these are monotonic. All of these functions are monotonic. They are very fast to compute. Specifically, the ReLU function is very fast to compute, right? The computation is very fast. And that's why, in many cases, by the way, that's what allows it to be more efficient in many cases. Do they cover the required output range? Sometimes, right? So again, sigmoid function will return values between 0 and 1. Might be very good at the final layer if you're trying to approximate probabilities. 10H provides values between -1 and 1. Might be relevant in many control functions. ReLU can provide values between 0 and infinity, right? So that might be relevant to, well, other cases where it might be relevant.